गुड आफ्टरनून एवरीवन। कैसे हैं आप लोग? हाउ आर यू एवरीवन? आई थिंक एवरीवन इज फाइन, हैव टेकन योर लंच एंड रिवाइज्ड the previous lectures as well. So today this is going to be the last lecture of Thermody. In the previous lecture or up to the previous lecture, we have completed the heat engine and calculated the efficiency of the heat engine in the previous lecture, if you remember that. What is a heat engine? Heat engine was a device or is a device which converts heat energy into some form of mechanical work. It has some source. There is a source of heat. There is a working substance, and there is a sink. So that was the three main components of the heat engine. I think you remember those things. Now, first of all, what is going to be our today's session? What we will study in today's session? Let's discuss. First of all, we will see a recall test. After that, we will discuss about reversible and irreversible processes. Then we will talk about some thermodynamics, second law of thermody, then Carno engine, and then efficiency of Carno engine. I think it is clear. So, first of all, starts with your recall test. Okay, so your recall test is on your screen. This is again going to be a very simple question. I think you should take not more than 40 seconds to solve it. 40 seconds will be enough. So let's start. You have 40 seconds. You can easily solve it out. Question says, a heat engine receives 50 kilocalorie of heat from the source. Now, if you remember the design of the heat engine, what it was like that. There is a source and there is a sink. That's how we represented the heat engine. This is source, this is sink, and it takes, according to the question, it takes some heat from the source, and that heat was 50 kilocalorie. I think that was the heat received, 50 kilocalorie. And some work is performed, and some heat is rejected. That's the case. Now, if you can see, the efficiency is given. Efficiency of 20% is given. Now, what if I say that what is the meaning of efficiency? Meaning of efficiency is how much heat energy is converted into work done. How much heat energy is converted into work done? You will say 20% of heat energy is converted into work done. That's the question is, na? What is the meaning of efficiency? How much heat energy? I will define it. What is efficiency? How much heat energy is converted into work? So they are saying efficiency is 20%. That means 20% of energy is converted into work done. I can use the formula that we have derived yesterday, but you can do it in your mind actually. So what will be the work done? Work done will be what? 20% of 50 kilocalorie. So work done will be, if you can calculate this, So work done will be 20% of 50 kilocalorie will be 10 kilocalorie. That's our answer. Work done is 10 kilocalorie. Okay, no problem. After that, they are saying the work obtained from the engine and the heat rejected to the sink. Now 50 kilocalorie is coming from the source. 10 kilocalorie work is done. Then remaining will be what? 40 kilocalorie. Remaining will be what? 40 kilocalorie. So heat rejected to the sink, if this is Q1 and this is Q2, then Q2 will be what? Q1 minus W, that is 40 kilocalorie. So which option is correct? Option A is correct. Which option is correct? Option A is correct. 10 kilocalorie. First of all, we need to write work done. Then we need to write heat rejected. So 10 kilocalorie and 40 kilocalorie, that will be the answer. I think it is clear now. That is a very simple question. You can remember this definition as well. You can remember this definition as well. Efficiency, definition of efficiency. What is the meaning of efficiency? Now moving further. Now, what is reversible process? This is again a very famous term. Most of the times people may ask you what is reversible and what is irreversible process. So now, if I explain it to you, if I describe few things, let's suppose this is a PV graph. Let's suppose this is pressure volume curve indicator diagram, and this is the curve. Let's suppose. Now, let's suppose the expansion is going on in the process A to B. Now, listen to me. While moving from A to B, there are various states of the system in between A and B. Like there is a state here, a state here, and a state here. There are lot of states in between A and B. Now, if I say just this is the expansion thing, na? From A to B, gas is expanding. Now, if I say compress the gas in such a way that while compressing, each of these intermediate state is repeated, then the process is known as reversible process. Or mind my words, while going from A to B, you followed a certain path, which is represented on the PV curve. Now, while compressing, if the PV graph or PV curve follows the same path in the reverse direction, then the process is known to be reversible process. I think clear this point now. So if I talk about in terms of definition, what is reversible process? Any process which can be made to proceed in the reverse direction, so that all changes occurring in the direct process are exactly reverse in the reverse process, is called reversible process. So no need to worry about that. What I'm saying, if you are expanding the gas from A to B, and again you are compressing the gas from B to A, and if the path followed on the PV curve is same, then the process is reversible. Clear? Now, one more thing that is to be noted here. If I say during the expansion, work done will be area under the curve. Work done will be area under the curve. And A to B, if you talk about, work done will be positive or negative. Can anyone answer? Is this work done going to be positive or negative? From A to B. A to B, there is expansion, and expansion work done is positive. That means work is done by the system. Now again, while B2A, if I talk about, then work done will be negative because compression is going on, and work done is negative and work is done on the system. Now consider two things that I am saying. In both the cases, magnitude of work done will be same because area will remain same. Area will remain same. So work done will be same from A to B or from B to A. Is it clear? Now, if work done will be same, then can we conclude that there is no loss of energy in the complete process? There is no loss of energy, or you can say there is no dissipative force there. No dissipative force is there, because if dissipative force were there, dissipative force, what I mean from dissipative force, the friction force, the viscous force, electrical resistances, these all are the dissipative forces. These dissipative forces must be absent. Only in that case, work done will remain same in both the forward and reverse process. So, what are the conditions for reversible process? Conditions are no dissipative forces should be present, because in the presence of dissipative forces, if some energy is lost, then that energy cannot be recovered. So what is the condition of reversible process? First condition is there is no dissipative force present. Dissipative force means friction, viscosity, electrical resistance. There are a lot of dissipative forces. Okay. Another thing is the process must be very slow. What is the meaning of process must be slow? If process is slow, only then you can define these intermediate states. For intermediate states to be defined, the process must be slow. Otherwise, these intermediate states will not be defined completely. So for this purpose, the process must be slow. So reversible process, I think it is clear. In reversible process, work done will be same. Work done will remain same because area will remain same. And what are the conditions of reversible process? That's also the same. Okay. Now, what is irreversible process? The opposite of reversible process are known as reversible process. So there is no need to discuss. I think you can see the definition. Any process I have placed only not in between, which cannot be made to proceed in reverse direction. That means the process which cannot repeat its path on the PV curve is known as irreversible process. I think it is clear. So we have considered reversible and irreversible process. One more thing that you should know, that any process in real life is not reversible, or you can say no process is reversible in real life. You can mention this line. This is an ideal concept. So no real process is reversible. Why so? Because you cannot eliminate the presence of dissipative forces. In whatever may be the situation, whatever may be the system, there must be some dissipative forces present. So you cannot eliminate those dissipative forces. You cannot eliminate friction. You can minimize friction, but you cannot eliminate. So no real process is reversible. That should be noted actually. Now, moving further. What is second law of thermodynamics? Second law of thermodynamics, there are two statements of second law of thermodynamics. One thing that I will assure you, or I will inform you more rather than assuring, that this class is aimed for the CBSE exams or your board or your class 11 CBSE exams, because as your exams are approaching, so this class is a bit oriented towards those CBSE exams. So try to inform your classmates as well that these classes are for the CBSE exams. We are not going in deep details as per the JE requirement. So Okay, let's start the session again. What is the second law of thermodynamics? There are two statements. What are the two statements? One is Kelvin-Planck statement. What it says, the statement is, it is impossible to construct a heat engine whose efficiency is 100%. This is a very simple and fundamental statement, you can say. It is impossible to construct a heat engine whose efficiency is 100%. Clear? Why they are claiming so? You can check that as well. For example, if I say, or you know that efficiency is what? 1 minus Q2 by Q1. I think it is clear. 1 minus Q2 by Q1. For efficiency to be 100%, Q2 should be 0. Q2 should be 0. Only in that case, efficiency will be 100%. Can you see that? Can you assume those things? Can you see that? If Q2 is 0, then eta will be 1. Then efficiency will be 1. 1 means 100%. So what is the meaning? Q2 should be 0. That means no heat is rejected. No heat is rejected. There is no need of sink. If sink is not needed, for example, this is our source, this is our sink, and I think you remember that this is Q1, this is Q2, and this is our work done. This is sink. So what are they saying? They are saying that Q2 should be 0. If this term is 0, then you can see that at any temperature of source, engine will work at any temperature of source, because there is a difference in source and sink. Na temperature difference. Source is at high temperature, sink is at low temperature. That's what we have studied. But they are saying that there is no need of sink. If there is no need of sink, then you just don't need to create a high temperature. There is no requirement of high temperature. In that case, there is no need to burning of fuel. There is no need of fuel burning. And you don't need to burn petrol or diesel, whatever the sources you are burning fuel. It will operate by air. You will say it will operate by getting heat from the surroundings, and it's just run like that. So it's not possible. You haven't seen those things often. So what I'm saying, it is impossible to construct a heat engine whose efficiency is 100%. That's what the statement of Kelvin-Planck. Kelvin and Planck were two scientists. They have individually given their statements, and the combined statement of these two scientists is Kelvin-Planck statement. Now there is another statement, Clausius statement. What is the Clausius statement? It says it is impossible for a device to transfer heat from a colder body to a hotter body without any external work. Have you ever seen that? That heat is being transferred from colder body to a hotter body. Like always heat transfer, what we have seen, what we have studied is heat transfer takes place from high temperature body to low temperature body. So what is the statement? Heat cannot be transferred from a colder body to a hotter body without any external work. And this external work you will see in refrigerators. In refrigerators, the inside temperature of the refrigerator is colder. It's lower than the surrounding, but still heat is being rejected to the surrounding because some external work is done by the compressor. External work is done by the compressor. So what is second law of thermodynamics about? It talks about the direction of heat flow. It talks about the direction of heat flow. So first of all, you need to remember those two statements of thermody. They are usually asked in your CBSE exams. Now again, moving further. there is a Carno engine. What is Carnot engine? This is again a heat engine. This is again a heat engine, which is designed by Carnot, a scientist, and he claims that this is the best efficient, yeah, or you can say most efficient engine possible, or theoretical engine possible. This is the most efficient theoretical engine possible. That's the claim of the Carnot. So let's check it. What is the efficiency, how it works, what are the cyclic process, or whatever. Okay. So first of all, let me talk about a few things. It operates in four processes. What I'm saying, it operates in four processes, or you can say four steps. One thing is clear. Second thing, all the heat engines operates in cyclic process. So operates in cyclic process. These are the small things that you should remember. And all the processes are reversible. All the processes are reversible. Now, consider the situation. Let's suppose this is a thermodynamic system. I will take a laser pointer. Let's suppose this is a thermodynamic system. The walls of the system are adiabatic. Listen to me very carefully. The walls of the system are adiabatic except the base. Except the base. Base is diathermic. Now, one thing is clear that walls of the system are adiabatic except the base. So, no heat can be transferred from the side of the walls. Only heat can be transferred from the base. Clear? Another thing. The piston is initially at A. The piston is initially at A. And in the first step, this thermodynamic system or cylinder is placed on a body at temperature T1. This temperature is constant. This temperature is constant. Clear? Now, the gas is allowed to expand. There is a gas inside it. Obviously, the ideal gas is inside it. And the gas is allowed to expand. I am talking about step one. This is four-step engine. So I am talking about step one. Gas is allowed to expand up to a point B. Now, can you see that when the gas expands, its temperature will slowly decrease. And if temperature will decrease, then extra heat will be provided. Extra heat will be provided from this source. And let's suppose Q1 heat is provided. The process is slow, extra heat is provided, so the temperature of the system is maintained and the process is isothermal. So what is first step? First step is the isothermal. Can you see that gas is expanding? So this is known as, first step is known as isothermal expansion. I think first step is clear. In the first step, this thermodynamic system is kept in contact with a high temperature body, which is generally known as source. Which is generally known as source. Clear? And during the expansion, some heat is taken from the source, and let's suppose that heat is Q1 and process is isothermal expansion. Now, in the next step, in the step 2, what's happening? Now the base of this high source is replaced by an insulating stand. This source is replaced by an insulating stand. Now all the walls are already insulating. Now base is also insulating. So can you see that no heat exchange will take place? If heat exchange is not taking place, then the process will definitely be adiabatic. Process will definitely be adiabatic. And the gas is allowed to expand from B to C. So this is again adiabatic expansion. Clear? So two steps are clear. In two steps, two processes were there. One is isothermal expansion, one is adiabatic expansion. We will draw a PV curve for the same. Now in the third step, what's happening? Now the gas is compressed. You can see first it is expanded from A to B, then from B to C. Now it is compressed from C to a position D. Clear? Now again you can see that the gas is being compressed and the base is replaced by a low temperature body, which is at temperature T2. And this is known as sink. This is known as sink. It is replaced by a low temperature body. During the compression, when you compress the gas from C to D, some heat is generated. And the heat which is generated is transferred to this system or to the sink. Let's suppose Q2 heat is being transferred to the sink. I think every point is being clear. But the system is in continuous contact. But the system is in continuous contact. Okay, what I'm saying, the system is in continuous contact with the temperature T2 or the sink. So its temperature will remain constant. And if temperature remains constant, then the process is again isothermal. What do you say? Is it compression or expansion? The gas is being compressed from C to D. The piston is being compressed from C to D. So this is again compression. So three steps were there. I have discussed. Now in the next or final step, the same process is repeated, or you will say this time the gas is again compressed from D to A. D to A. D, and what is A? A is the starting point. So this is the complete cyclic process. A is the starting point. Gas is again compressed. Now you can see that everything is insulating. So the process is adiabatic compression. So there were four steps or four strokes, you will say. Sometimes people say, call it as four strokes. This is step 3. And this is again a step 4. So this is the thing which is happening. Two processes are isothermal and two processes are adiabatic. This is what Carno engine, how it works. Now, what is a Carnot cycle? The representation of these strokes or these steps on a PV curve is known as Carnot cycle. What is Carnot cycle? The representation of these processes on what? PV curve. Now suppose, now you can see that. First of all, there is an isothermal expansion. A to B, there is isothermal expansion. B to C, adiabatic expansion. C to D, isothermal compression. And D to A, adiabatic compression. I think everything is mentioned here. This is Carnot cycle. Now, one thing, can you see that during the process A to B, during the complete process A to B, temperature is maintained at T1. During the complete process C to D, temperature is maintained at T2. where T1 is the temperature of source, T2 is the temperature of sink. You can see that T2 is the temperature of sink, T1 is the temperature of source. I think it is clear. Now again, you can see that again during the process or during the step 1, Q1 heat is given to the system. Q1 heat is given to the system. So I will mention it as Q1 heat is given to the system. During the process CD, what we have assumed that Q2 heat is rejected by the system. So I will mark it here. Q2 heat is rejected by the system. This is your Carnot cycle. You need to remember it because it is directly asked in your exam. Two processes are isothermal, two are adiabatic. Now again, moving further. If I talk about what is the efficiency, this is again an important derivation. You will say it will take some 5 to 6 minutes. I think everything is clear till now. JNV Bhavnagar, JNV Sangli, JNV P, P for I think Pune, right now. So, okay, what is the efficiency of Carnot engine? In the yesterday's class or in the previous class, what we have discussed that in a cyclic process, the efficiency is if I talk about the efficiency is 1 minus Q2 by Q1. This has been already discussed in the previous class or in the efficiency of heat engine that whenever there is a cyclic process, the efficiency will be 1 minus Q2 by Q1. Here Q1 is what? This is Q1 and this is Q2. I think you know these things. Now again, I am assuming few more things here. Let's suppose the pressure and volume at A is P1 V1, at B P2 V2, here P3 V3, and here P4 V4. We have considered some values here. Now, one more thing that you know that during the process A to B, temperature was maintained at T1, and during the process C to D, temperature was maintained at T2. Clear? Okay. Now I am assuming one more thing here that let's suppose during AB, work done is W1, during BC, work done is W2, here work done is W3, and here work done is W4. I am assuming the work done in each process. Okay. Now listen to me. If I find the value of Q1 and Q2, then I will be able to find the value of eta, find the value of, I will be able to find the value of efficiency. So I am going to solve for the Q1 and Q2. Now listen to me. For the process AB, if you see AB is the process which is going to be an isothermal process. This is isothermal process. And if this is an isothermal process, then you will say that delta U will be 0. Can you see these lines? See the flow of these lines. Delta U will be 0. And if delta U will be 0, then you will say that Q1 will be, what is the formula? Q is equals to delta U plus W. Can you see that delta U is 0? So what we can write that Q1 is equals to W1. Is it clear? Q1 is equals to W1. Again, if I say What is the work done in the isothermal expansion? You need to remember those formulas. Work done in isothermal process. W is equals to nRT ln V2 by V1. I think you have remembered the relation. nRT ln V2 by V1. This is the work done in isothermal process. So in this way, we have calculated Q1. Now, one thing to be noted, the temperature which is constant is what? During the process AB, the temperature is what? T1. T1. Let's suppose this is equation number 2. So we have calculated Q1. Now we need to calculate Q2. For that, you need to consider which process? You need to consider CD process. Again, for process CD, this is again isothermal. What is this isothermal? Compression. Again, if the process is isothermal, then delta U will be 0. So what you can write, Q2 is equals to W2. W2 is what? nRT2. The temperature is what? T2. ln final volume by initial volume. Final volume from C to D is what? V4 by V3. Now, one thing that you should know, that during the process C to D compression is there, and in the case of compression, work done is considered to be negative. So can you place a negative sign here? Yes, we can place a negative sign. Now I am transferring this negative sign. Then Q2 will be nRT2 ln. If I transfer this negative sign inside the ln, it will become V3 by V4. Let it be equation number 3. I think it is clear till now. We have calculated Q1, we have calculated Q2. Now place these two values in equation 1. Okay, I'm placing the values. From 1. Eta will be 1 minus Q2 by Q1. Q2 is what? nRT2 ln, we can check it, nRT2 ln V3 by V4. V3 by V4 divided by Q1 is what? nRT1 ln V2 by V1. Clear? Now something will get cancelled. NR will be cancelled. So eta will be what? 1 minus T2 ln V3 by V4 divided by T1 ln V2 by V1. Let it be equation number 4. Now, one more thing that you should consider here. I think that is again a very important thing that is going to be our punchline here. Okay. Now consider the process B to C. B to C is the adiabatic process. B to C is what? Adiabatic process, and what we have seen here, this is P1 V1, this is P2 V2, this is P3 V3, and this is P4 and V4. The temperature here is T1, the temperature here is T2. Now, B2C is adiabatic process, and for adiabatic process, what we know that T1 from B to C I am talking about. Do you know the relation that T into V raised to the power gamma minus 1 is equals to constant for adiabatic process? So I am placing the values in this relation. Temperature at B is T1, volume is V2. V2 raised to the power gamma minus 1 is equals to, at C, if you talk about temperature is T2, volume is V3 raised to the power gamma minus 1. So can you see that T1 over T2 is equals to V3 over V2 raised to the power gamma minus 1? Let it be question number 5. You need to put these values to get a desired result, to get a better result, which is more feasible. This is for process BC. Now, again, if I talk about for process D2A, this is again adiabatic. D2A is again adiabatic process. In the D2A process, you can again apply this formula. You need to know how to apply this relation. At point D, the temperature is what? T2. At point D, temperature is what? T2. So T2 into volume is what? V4 raised to the power gamma minus 1 is equals to, at point A, temperature is T1 into volume is V1 raised to the power gamma minus 1. Again, you can calculate that T1 over T2 is equals to V4 over V1 raised to the power gamma minus 1. I think this step is again clear. From equation 5 and 6, you can see that LHS is same. So RHS will also be same. So I am going to comparing 5 and 6. If you compare 5 and 6, what you can see that V3 over V2 is equals to V4 over V1. Is it clear? Or you can see that V3 over V4 is equals to V2 over V1. Now, V3 over V4 is equals to V2 over V1. If I place this value in equation 4, then V3 over V1 is equals to V2 over V1. So these two terms can be cancelled out. So what will be the value of eta? Then eta will be, or efficiency will be 1 minus T2 by T1. This is going to be a very important result. Efficiency will be 1 minus T2 over T1. That means efficiency of a Carnot engine is independent of the working substance, because there is no need or no requirement of the working substance that which quality the working substance has. It only depends on the temperature of sink and temperature of source. So in this relation, what you need to remember that what is T2? Temperature of sink. What is T1? Temperature of source. That means efficiency of a Carnot engine depends only on the temperature of source and temperature of sink, and is independent of what? Repeat with me. And is independent of what? Working substance and the amount of heat it has taken, Q1 and Q2 it has taken and it has rejected to the sink. It's independent of all these things. I think the point is clear. I have no such place to write. You can write it by yourself. The thing is, this is the simple question that may be asked in your objective question or your multiple choice question, that efficiency of Carnot engine is independent of working substance. Clear? And depends only on the temperature of source and sink. Clear? So what is Carnot's theorem? This is again a very simple term. That's what I'm saying till now. All reversible engines operating between the same two temperatures have equal efficiency irrespective of the working substance. That's what I'm saying. And this is known as Carnot's theorem. So he don't have much knowledge actually. That's what we are discussing now. We are discussing the same thing. That you can see that it's not a big deal actually. I think it is clear. Okay, moving further. There is a concept test. I will give you one question and you need to solve it out. After that, we will wrap up the class. And I will give you one homework question. This is a very simple fundamental question. This is just a calculation based question. Calculate the approximate thermal efficiency of a Carnot engine working between ice and steam point. Okay, this is very fundamental question. I need answer actually. You don't need to calculate exact value. You need to answer it approximately. Okay, JNV, Warangal, Sangli, Pune, Mehsana, Bhavnagar. Everyone should answer. The persons who are live on YouTube can also answer. It will not take a lot of time. It will be very easy question. You just need to put the values. Okay. So what is the efficiency of a Carnot engine? You will say one efficiency is what? 1 minus T2 by T1. Again, try to remember what is T2? Sink temperature. T1 is what? Source temperature. How can you identify source and sink? Source is of high temperature. Sink is of low temperature. Sink is of low temperature. So there are 2 points. Two temperatures are given, ice point and steam point. So ice point will be our sink because it is a low temperature. So ice point, or you can say sink temperature will be T2 is equals to 0 degree Celsius. And T1 is equals to what? Steam point, that is 100 degrees Celsius. But whenever you deal with it, you need to put the temperatures in Kelvin. So 0 degrees Celsius will be written as 273. It will be written as 373. I think you know the concept on a degree Celsius to Kelvin. You need to add 273. I think this point is very much clear. This is being taught from the class 6, 7th or whatever. So you just need to put the values. If I put the values, what I will get, efficiency is 1 minus 273 divided by 373. And if you calculate it, you will get approximately 0, okay, whatever it is, 0.2681 approximately. I have calculated it using calculator, but you need to calculate the approximate result. This is the value of eta. If I talk about percentage, you need to multiply it by 100. So it will be approximately 26.81%. So 26.81%, this is going to be answer of option D. This is our option. Now I will give you one homework question. Try to solve it out. And in the next session, we will start oscillation. That is again a very important question, very important session actually. So this is your homework question. This is again a very simple question. These are the question of CBSE level. This is 27 degrees Celsius. So try to note it down and we are going to end the session. Let me know what you feel about the classes. Try to revise your concept, score good in your exam. That's what I can say. So bye everyone. We will see you again in the next session. We will